let's look at this paper. Okay, paper 1, okay, from variant 1-2, okay, so which is going to be October, November 2022. So the first question is, why is the first ionization energy of phosphorus is greater than the first ionization energy of silicon? Okay, so when we look into that, okay, you can just remember all SIPs, yeah. So aluminum, silicon, phosphorus, and sulfur, they are all in the same row. So if you look at it, okay, the phosphorus atom has one more proton in its nucleus. Okay, let's say if you do not know, okay, let's move on to the rest. Like for example, if B, the atomic radius of a phosphorus is greater. So if you look at phosphorus compared to silicon, okay, when you go across the periodic table, okay, we know that the atomic radius becomes smaller and smaller. Yeah, so this is one of the things that you can remember. So when they become smaller, so you can see the phosphorus atomic radius is smaller compared to silicon. So therefore, this statement is wrong. And then if you look at C, the outer electron in phosphorus is more shielded. Okay, this statement is not true because it's in the same row, so they have the same number of shells. So they are not shielded. They are shielded almost constantly. So they are not shielded. Yeah, so similar shielding. So that statement is also wrong. The outer electron in phosphorus is paired. So if you look at phosphorus, phosphorus is 15. So 1s2, 2s2, 2p6, 3s2, and 3p3. So if you look at this 3p3, okay, so all these electrons are going to be in its orbital. Okay, so they are going to be singly filled. Yeah, singly filled. So they are not paired. Okay, so therefore this statement is also wrong. And if you look at A, the phosphorus atom has one more proton in its nucleus. That's true because across the periodic table, okay, the phosphorus has one extra proton. So this extra one proton, they will increase the nuclear charge, and this will actually make the attraction towards the from the nucleus to be greater towards the electrons. So it will hold the electrons closer to the nucleus. Therefore, it's much more difficult to remove the electrons from the phosphorus compared to silicon. So that will be the best answer for this question number 1. Okay, so answer is A. Now for number 2, sodium peroxide, okay, is used to absorb carbon dioxide, okay, and release oxygen in closed environment such as space capsules and submarines. So they have given us the equation. So they are asking which mass of sodium peroxide will be required to remove 2.4 dm cube of carbon dioxide from this atmosphere at room temperature and pressure. So we know that, okay, 1 mole of any gas occupies 24 dm cube, yeah, of volume. So if you have 2.4 dm cube, 2.4 dm cube is going to be, so this one divided by 10, so this one should be divided by 10, so that's 0.1 mole. Yeah, so we are looking into 0.1 mole of carbon dioxide. Okay, so if you have 0.1 mole, so if I just put 0.1 mole over there, so we want to find out what is the mass of sodium peroxide. This is sodium peroxide, so this is 2 to the ratio of 2, so same ratio, so this will become 0.1, 0.1. Okay, that's going to be the number of moles. And if you look at, we are looking for the mass, so number of moles equals to mass over mr. Okay, so relative molecular mass, so number of moles is 0.1, the mass is what we want, the mr. Sodium is going to be 2 times 23, take note, yeah, this one we are not going to include, so we are just going to focus on this. 2 times 23, and then oxygen 2 times 16. Okay, so you will have 0.1 equals to mass 46 plus 32. So that's going to be mass divided by 78 equals to 0.1. Mass is going to be 0.1 times 78. That's going to be 7.8. So the answer is going to be 7.8 gram. Yeah. So the next question is, in which species are the number of proton, neutron, and electrons are all different? So we just look over here. Proton is going to be 13. We look over here. So electron must be the same. Okay, so 13. And neutron is the difference. So 27 minus 13. So that's going to be 14. Okay, so they want all different. So this cannot be the answer. So if you look over here, proton is 17. electron is going to be supposed to be 17, but because this is negative ion, so extra one more electron, so it's going to be 18 plus one more electron. And neutron is going to be the same, 35 minus 17, so you are going to get 18. Okay, so therefore this is also wrong. They want all different. And then same for proton, 16, electron supposed to be 16, but you have 2 minus, so it means extra 2, so 18. Neutron is going to be the difference, 32 minus 16, that's going to be 16, so this is also going to be wrong. And this one, proton is going to be 19, electron supposed to be 19, but because positive 1, they have lost 1 electron, so 18. Neutron is going to be 39 minus 19, that's going to be 20. So you can see all of them are different, therefore the answer is going to be D. Yep. So the next question, number 4. Okay, calcium oxide and magnesium sulfide each react with acid. Okay, so magnesium sulfide each react with acid. Okay, so if you look at it, there are two equations over there. Okay, so okay, we will look at it differently as well, separately as well. So a mixture of two compounds X, okay, this X contains calcium oxide and magnesium sulfide. So they react exactly with 0.125 mole of dilute hydrochloric acid. So if you have dilute hydrochloric acid, they will give you H plus and Cl minus. So if you have 0.125, therefore they have 0.125 mole of H plus as well. Okay, so the amount of hydrogen sulfide formed is given. Okay, so what we do, okay, if you look analyze at these two equations, so this one, the only equation that has H2S is going to be 0.0250 over here. So if you have 1 mole, yeah, so we look at this equation first, yeah. So if you have this H2S, okay, so what we want to do, we want to find out what is the mass of calcium oxide. So we need to relate to the first equation, yeah. So what we can do first is to find the H plus, okay. What is the number of moles of H plus? So what we can do is with the ratio of 1 to 2, so double. So we have 0.0250. So this one will be 2 times 0.025. That's going to be 0.05, okay, moles of H plus. Okay, so do not confuse that this is 0.05. This is also going to be 0.05. That's wrong. Yeah. So what we can do now is, okay, we know that the acid, okay, that we used earlier was 0.125 is given. Yeah. So the H plus 0.125. So we can find out if you have 0.05 over here, of course the remaining amount of acid must come from here. So how do I find that? Okay, you can find that from 0.125, you minus with the one that you have now, 0.05, okay, and you will get okay, let's actually calculate 0.125, okay, minus 0.05, and you will get 0.075, okay. So once you have that, okay, we'll just put it over there, 0.075, and we can calculate now what is going to be the calcium oxide. Yeah, so calcium oxide, you see again 2 moles, 1 mole. Yeah, so this should be 0.075 divided by 2. That's going to be 0.0375, and we are looking for the mass. So number of moles equals to mass over mR. Okay, number of moles is 0.0375. Okay, mass is what we are looking for. Calcium oxide, calcium is 40.1, oxygen is 16. So you can find the mass as 0.0375 times, okay, 56.1, and you will get, okay, times first 56.1, and you will get 2.10, yeah, 2.10 gram. So that's going to be our answer over here. Okay, now next, okay, you have 2 moles, okay, of VO2 plus, okay, 2 moles, okay, react with 1 mole of zinc atom, okay, in the presence of dilute acid. So I'll just put in the presence of H plus, okay, you can put it in the equation or what, okay, doesn't matter. So the product includes zinc 2 plus and Y, and this Y can be something that contains vanadium. So basically it can be any of these three. Yeah. So they say only zinc and vanadium change oxidation state in this reaction. So it means H plus do not change any oxidation state. So we'll just leave it over there. So now, okay, we have to use this concept, okay, of balancing equation using oxidation number. Yeah. So if you are not sure about this, maybe you can check my YouTube channel. Just type how to balance equations using oxidation number, and I have a few videos to show you on that. Okay, but now I'll just show you. Basically the concept is, okay, if you want to change zinc to zinc 2 plus, you are losing, okay, you're losing 2 electrons over there. Okay, so 2 electrons is being lost, and the concept is, if you move over here, okay, there should be the same amount of electrons, okay, or the same ratio should be found over here. So but the only thing is, okay, here they have times by 2. This one is 1. Yeah, so if they have times by 2, so we just put 2. Why they try times by 2, okay, or any number? Because they want to make it as the same number of electrons. Okay, the amount of electrons lost must be the same as the number of electrons that's gained. So if something times by 2, and we know that this is 1 mole, they already say 1 mole, it means must be 2 electrons being lost only. So what times by 2, yeah, why 2, this number, what times by 2, okay, give us 2 electrons. So of course you can see it's 1. Yeah, so it means this is going to be gain of 1 electron. Okay, gain of 1 electron. So where what this will help me, okay, it will actually tell me that, okay, from VO2 plus, okay, when they change it to something, okay, what happens? Okay, they are gaining VO2 plus, they are gaining 1 electron. So if you look at this oxidation number of vanadium over here, so you can just put X, so 2 times negative 2 oxygen, so equals to plus 1. So X is going to be plus 1, so you bring it over there, so plus 4. So that's going to be oxidation number is 5. And we know, okay, from here, the oxidation number of 5, when they gain electron, 1 electron, so they're supposed to change from 5, because 5 plus electron, 1 electron, the oxidation number, yeah, the electron is negative 1 charge. So it's going to be 5 plus minus 1, so that's going to be 4. So it means that this Y, or the ion that contains the vanadium over here, the oxidation number of vanadium must be plus 4. Okay, so we need to find out which one has plus 4. Okay, so we are just be careful. Okay, it's not from 5 to become 6. Okay, it's 4 because electron is negative 1. So we are going to look for any answer, okay, that can give us plus 4. So if you look at this, X, okay, 3 times negative 2, so negative 6 equals to negative 1. X equals to negative 1 plus 6, so that's going to be 5, not our answer. So X minus 2 equals to plus 1, so X equals to plus 1 plus 2, that's 3, so not our answer. We are looking for plus 4. So X minus 2, okay, equals to plus 2. So X equals to plus 2 plus 2, so 4. This is what we are looking for. So X minus 4 equals to plus 2. X equals to 2, then plus 4, that's 6. Not what we are looking for. So therefore, the answer is going to be C, because vanadium, VO2 plus, okay, has the oxidation number of 4, okay, for vanadium. Yeah. So that's going to be our answer for this question. Okay, next, okay, number 6. Okay, for number 6, okay, the compound potassium bismutate is a powerful oxidizing agent. What is the significance of V or 5, okay, in potassium bismutate? So basically, if you have potassium manganate, yeah, potassium manganate, we just say potassium manganate 7. Okay, so potassium manganate 7 basically tells us that the manganese ion, yeah, the manganese atom, yeah, in this KMnO4, okay, the oxidation number is plus 7. Yeah, so that is going to help us to identify. Like, let's say for example, if I have iron 3 oxide, okay, iron 3 oxide is Fe3 plus, okay, because the oxidation number Okay, they are showing for the one that is directly after iron, then oxidation number comes. So the 3 show us for the oxidation number of Fe, and then oxygen 2 minus, so we write iron 3 oxide as this one times 3 times 2, so Fe2O3. Yeah, that's going to be iron 3 oxide. So let's come back over here. So they say, what is the significance of 5 of potassium bismutate? So the 5 is beside here bismutate. So this is going to be the ion BiO3 minus ion. So the 5 tells us the oxidation number of Bi atoms in that ion. So if you look over there, it is the oxidation number of bismuth atom. Yes, correct. Okay, it's the charge of bismutate ion. The charge of bismutate ion, this is bismutate ion. So the charge of bismutate ion is -1, not 5. Okay, therefore this is wrong. The oxidation number of bismutate ion, is also -1. So no. Okay, we just follow over there. It's a sum of charges of 2 ions present. The 2 ions sum of charges is 0. Yeah, +1 and -1, 0. So no. Yeah, the 5 is just telling us the oxidation number of bismuth atom. So which is this one. Okay. Now, number 7, hydrogen peroxide. Okay, decomposes slowly. Okay, to form water and oxygen. The reaction is faster when the catalyst is present. So they are asking which statement is correct. So please remember, okay, KC is only affected, KP and KC, equilibrium constants. They are only being affected when there is a change in temperature only, yeah. So pressure, concentration, catalyst, they do not affect the KC values, yeah. So which statement is correct? The catalyst alters the Boltzmann's distribution, so the reactant molecules have more energy. That's wrong, yeah. So because catalyst, if you look at the Boltzmann's distribution, so total number of particles, okay, total particles, and then energy. Okay, so when we draw the graph, okay, Boltzmann's distribution, so generally if you have the activation energy is around here. So they say catalyst, when you put catalyst, if let's say you put catalyst, what will happen? The activation energy is going to become lower a bit. So EA, okay, of the catalyst will be somewhere here. So, but nothing happens to the shape of the curve of the Boltzmann's distribution. So therefore, this one wrong, yeah. So the catalyst has no effect on the value of Kc. Just now I told you, yeah, this is correct. Okay, catalyst has no effect. Only temperature has effect towards Kc. The catalyst increases the value of Kc. Wrong. The catalyst provides a different reaction mechanism, yeah, probably, but with lower activation energy. So this is also wrong, yeah. So the answer is going to be B. Now, just extra information over here. If let's say I am dealing this is going to be temperature 1, and I want to draw, okay, the Maxwell, the Boltzmann's distribution for temperature which is going to be higher, yeah, what we are expecting. The graph that we are going to expect to move, yeah, higher temperature, it will move to the right, okay. So, and then, okay, the peak will be lower than, okay, the original peak. So you will have something like this, okay. So you will have T2, so T2 is greater than T1, okay. So if they ask you to draw, yes, please make sure you draw the area under the curve. Okay, under the graph tells us the total number of particles in that system. Yeah, so please take note of that. Okay, next. So number 8, a dimer Q is stable when solid. Okay, but dynamic equilibrium is set up in the solution. So you have this equation. So a solution Q has an initial concentration of 0.5 mole per dm cube. When equilibrium has been reached, the Q has fallen to 0.25. Okay, so it means Q becomes 0.25. So let's actually look at Q from 0.5 to become 0.25. Okay, Q is correct. 0.25. Okay, then becomes 0.25, 0.25. Okay, for Q is correct. Now we are going to look into R. Yeah, so if you look at R, okay, you see Q and R. Okay, every 1 mole, okay, you can see the ratio. Every 1 mole will give rise to 2 moles of R. Okay, so it means that a decrease of 1 mole of Q, for example, will give rise to 2 moles of the product of R. Okay, so therefore, you need to understand that, okay, they are not going to follow this particular graph. These two graphs are incorrect. Why it is incorrect? Because, okay, they are telling that, okay, the increase and decrease is going to be with the same ratio. These two graphs will be correct only if we are talking about Q directly changing to R. Okay, so this one, okay, will be correct. But in this case, okay, because every 1 mole of decrease, that it will have increase of double. So you see, in this case, from 0.5 become 0.25. There is a decrease of, okay, negative, okay, the change is negative 0.25. So it means here the increase should be positive, okay, double. So it should be positive 0.50, okay, double. So if you look at that, in the beginning, R is going to be 0, okay, but now the R is going to become 0.50. So let's actually look at, okay, here. So you see the R is going to be from 0 will become to 0.50. Okay, so these two graphs possible to be correct. But let's see, in this case, they are asking for KC. What is KC? KC is going to be concentration of the product, which is R, to the power of 2. Okay, and then divided by concentration of Q. So if you look at this, okay, if I just bring this down, okay, so we just calculate over here. So KC, okay, if I want to calculate what is the KC value, KC in this case is going to be concentration of R is going to be 0.5 to the power of 2, and then I divide by Q. Q is going to be 0.25, okay, 0.25. If I divide, I will get 1 as my answer, which is correct here. Okay, so this one 2 is wrong. Okay, therefore, okay, the answer is going to be C. Yeah. Now, next question. The reaction pathway, okay, for the forward reaction of a reversible reaction is shown. So which statement is correct? So just be careful with this. So this one we will take it as reactant and product forward reaction. So let's focus on the forward reaction first. The forward reaction, the enthalpy change. So enthalpy change in this case, from reactant to become product, they lose about 50 kilojoule. So the delta H is going to be negative 50. So in this case, the enthalpy change positive 50 is wrong. Yeah, so that is wrong. And then the enthalpy change for forward reaction is 30 also. That is wrong. It's supposed to be negative 50. Okay, so I'll erase this part. Now let's actually look at reverse reaction. Yeah, so reverse reaction, it means we are going to change this, okay, from the product. Okay, it's product now. This one is going to be reactant. This is going to be product. Okay, now, so they say the activation energy for reverse reaction. Activation energy from the reactant to the top. So the reactant to the top, we can see 50 plus 30. So the activation energy should be a positive 80. So this is correct. Okay, and then the enthalpy change for the reverse reaction. Enthalpy change for reverse reaction, reactant to product. So supposed to be positive 50 only, yeah, from here to here. So positive 50. So this one positive 30 is wrong. Yeah, so the answer is going to be A. Okay, for this. Now next question, number 10. So the enthalpy changes for positive possible reactions are given, and then they are asking about the activation energy. Yeah, so here you we can see, okay, if you look closely, okay, this reaction, okay, is actually a reversible reaction. It's just W and X, they are related. Okay, so it's the other way around. Okay, so that's why you see negative 56, positive 56, and then here also HI to HI to HI, the other way around, they compare. So here they want us to compare the activation energy. So let's actually compare W and X first. Okay, so let's say I'm drawing the graph, yeah, from the view of W. Yeah, so let's say for example this one is negative 56. So let's say for example I have this, and then it's an exothermic reaction, negative 56. So let's say this is sodium hydroxide and ACl. Okay, so this one, okay, negative 56. So let's say I'm just putting this, my activation energy, as X. Okay, So here they are talking about activation energy. So the activation energy for W, this reaction, so it's just X, okay, activation energy. But how about the activation energy for reaction X? So the activation energy is the other way around, yeah. So if I put sodium hydroxide, so instead of sodium hydroxide over here, I put the sodium hydroxide over here, and then ACl, okay. So it's going to be gaining, yeah, from here to here, so plus 56, okay. So anyways, okay, if you look at the activation energy, okay, for the reverse reaction, the activation energy should be from the reactant, which is from here all the way to the top, yeah. So that's going to be X plus, okay, X plus 56. So we can clearly see here the X, the activation energy, the X over here, the activation energy is greater than W. So you can see X greater than W, X greater than W. So these two statements are wrong. Yeah, we are going to reject that. Now we will do the same thing, yeah, for Y and Z. Okay, so I'll erase this part. So for Y and Z, similar. Okay, so let's start. I'll just focus from Y first. So it's positive. So endothermic reaction. So let's say, for example, endothermic reaction. So I have 2HI over here, and then H2 and I2 over here. So this one is going to be positive 11, and then I'll just take it as X over here. So the if I look at this in form of activation energy, of course, activation energy is from the reactant to the top. So it's supposed to be everything, yeah. So X plus 11. And if I look at it, if let's say reverse will react the other way around. So if this is the reactant, okay, and then I am going to look from here, okay, the activation energy is from the reactant to the top. So activation energy is only X. So if I compare, okay, which one is greater, okay, the one that is greater over here is going to be, of course, Y. So Y is greater than Z. So Y is greater than Z. So the answer is going to be Y. Yeah. Now, next question. Haber process is carried out with nitrogen partial pressure 50 and a hydrogen partial pressure of 150, temperature 400, ion catalyst. Yeah. If all the other conditions are kept the same, which one will result in raised activation energy? Now for activation energy, in this case, please remember partial pressure, yeah, pressure, temperature, yeah, they don't affect the activation energy. The only thing that I can see that will affect the activation energy is the ion catalyst. So they want raised activation energy, okay, nothing to do with this. So if you remove ion, so if you remove catalyst, of course, catalyst provides an alternative pathway, okay, where it has a lower activation energy. But if you remove the catalyst, of course, the activation energy will be higher. Yeah, so this will be the answer. Okay, the others, okay, will not be the answer. Yeah, so the answer is going to be boy. Okay, next question, number 12. Now the compound, okay, has simple molecular structure. Which statement about this compound is correct? Okay, so if you look at this compound, okay, you can see nitrogen. Something to note about nitrogen, because nitrogen is going to be 15, so 285, okay, in the simple form, okay, 5 valence electrons. So normally if you have 5 valence electron, so nitrogen, if you just look at it in this way, nitrogen, if you bond it to 3 CH3, of course, 3 valence electron is given reacting over being shared with the carbon, and then there will be one lone pair, okay, that will be existing at the nitrogen. And then for AlCl3 aluminium, okay, they have, okay, empty orbitals that can accept, okay, the electrons. Okay, this one you should know because we learned dimer, yeah, AlCl3, can form dimer with Al to become Al2Cl6. Yeah, so you should know, yeah, aluminium has orbitals that can actually take in the electron pair. Yeah, so dative bonding can be formed. So if you look at it, yeah, so what actually happens is the nitrogen, the electrons will be shared, okay, through dative bonding, okay, to this aluminium to form this, and then this CH3, CH3, and then CH3. Okay, so you will have this structure. Okay, so we are going to answer the question based on that. So they attract each other by hydrogen bond. No, there is no hydrogen bond over here. Why? Because hydrogen bond is the bond between hydrogen with NOF. Yeah, so I don't see anything over there. Okay, so the aluminium atom has incomplete valence shell of electron. Okay, so the aluminium over here, okay, they are complete now because they are receiving the electrons. Okay, and okay, the bonds around aluminium are planar. Okay, if you look at over here, there are total of 4 bonds. Okay, 4 bonds. If you look at 4 bonds, it means we are looking at tetrahedral. So it's non-planar, yeah, because tetrahedral is the 3D structure. Okay, so it's non-planar. Okay, wrong. Yeah, the molecules contain coordinate bonding. Yeah, as I told you, it contains coordinate bonding. Okay, or dative bonding. Yeah, so the answer is going to be D. Now 13, VSEPR theory should be used. Yeah, for any questions related to this, yeah, you just simplify. Okay, you just put the oxygen, you put oxygen, you put oxygen. So you can see this one double bond, just put double bond, and then this is single bond, just put a single bond, and then around this oxygen there is one lone pair. So if you want to solve anything to do with this VSPR or predicting the bond angle, you just make sure that the double bond, okay, we consider as single bond. Yeah, so how? When we count, so I'll just take this as 1. Okay, we don't count it 2, so I'll take 1. This is 1, and then we will count the lone pair as 1. So basically this is supposed to be 3 bonding pair, something like 3 bonding pair. Okay, so 3 bonding pair, generally we are looking into 120 degrees. Okay, trigonal planar, but in this case we are looking into 2 bonding pair and 1 lone pair, so it's a variation. Yeah, so roughly if you have 1 lone pair over there, so when this is replaced by 1 lone pair, what happens? Okay, the repulsion, okay, between the bonding pair and the lone pair will be greater compared to bonding pair and bonding pair. So it will become, this particular part will become more than 120, making the bond angle over here will become less than 120. So the idea is definitely it's not going to be 120. Yeah, it will be less than 120. But there are 3 answers over here with less than 120. Which one should we choose? Now, in that case, you need to remember, okay, ammonia, the bond angle, 3 bonding pair, 1 lone pair. Okay, the bond angle is 107 degrees. And water, okay, 2 bonding pair, 2 lone pair. The bond angle is 104.5. And then CH4 being 4 bonding pair, and then the bond angle is 109.5. So generally this one will not be suitable because it's already for 4 bonding pair. Yeah, so we are talking about total of a maximum 3 bonding pair, so it cannot be going to the extent of 4 bonding pair. So this one is definitely wrong, and if that is wrong, definitely this will be wrong. Yeah, because this is 107 is a variation, yeah, of this 4 bonding pair also. Yeah, so it cannot be that. Okay, so the only best answer that we choose over here, less than 120 and then more than 109.5, should be this one. Okay, so therefore that's the answer for this molecule for ozone. Now 14, each of the substances shown is gas which one most likely to show ideal behavior. So if you want something to show an ideal behavior, so they must have, okay, they must be far away from each other, so that, okay, the distance is far, okay, compared to the radius, so that the volume of the molecule itself is negligible, and also the bonding, yeah, there is no intermolecular bonding between them, so because of the distance. So how do we achieve that? Okay, pressure, okay, generally must be very low, yeah. If we have higher pressure, they are going to be closer to each other, so it must be a very low pressure. And temperature should be high, yeah, because if you have more temperature, it means the kinetic energy will be more, they are going to be separated more, far away from each other, so that's going to be ensuring ideal gas, yeah. So if you look over there, okay, if I want higher temperature, so this one cannot be this, and then I must have lower pressure. So lower pressure, if you compare, this must be the best answer. So the answer is going to be nitrogen, yeah. So next question, which one represents the variation of pressure volume of ideal gas? So whenever they ask you about this, just remember the formula PV equals to nRT, and then they are referring P and V, so you just put P equals to nRT divided by V. So the graph should be, if V means nRT and then 1 over V, yeah. If you have a graph P and then 1 over V, then the graph will be a straight line like this, yeah. But in this case, if you just have V over there, okay, so this one is P directly proportional to 1 over V, so it means this is a reciprocal graph, so graph should be this one, okay. So this should be the answer, okay, D. Now, okay, so the next question, 16. So they gave you some values, and then we want to calculate the enthalpy change for this, okay. So what we can do, okay, if see first, okay, from the equation, whether you can play around with the equation and get this, yeah. But when I look over here, there's no C2H6, 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 yeah, so we cannot play around, yeah. So we have to use a different strategy over here. So what we can do is, okay, we just know that, okay, this one is bond breaking, okay, and then this one should be bond formation. So total enthalpy, yes, of course, bond breaking plus bond formation, but do remember bond breaking is always plus, bond formation is always negative. So here there is for carbon and hydrogen, yeah, the 2 atoms of carbon, and then 6 atoms of 6 moles of hydrogen. They are already already broken, okay. You do not need to break it anymore, okay. So 0 and 0, there's no energy required to break them. So overall, the energy for bond breaking is 0. Okay, I put plus because it must be, overall must be plus, yeah. Now for bond formation, I have C, hydrogen, hydrogen, hydrogen. So I need to figure out, okay, how do I have let's say the bond between carbon and carbon, yeah. So I have the bond between carbon and carbon, 350. Okay, 350, do remember bond enthalpy means bond energy required to break the bond, yeah, but this one is bond formation, so cannot put plus 350, yeah, it must be negative 350. Please remember it's bond formation, yeah. So negative 350, and then we are looking for the bond between carbon and hydrogen, and we don't have anything to do with carbon and hydrogen over here, so we need to figure out something else. How do I get the bond energy between carbon and hydrogen? So if I look at carbon and hydrogen, I cannot use this. I cannot, in this case, I cannot use this, okay, and then I cannot use this. I think the only thing that I can use is this equation, okay, because CH4, okay, when they break, okay, CH4, when they break into 1 carbon and then 4 hydrogen, the energy is 1648, okay. So I can actually find out the 1 the energy required to break the bond between carbon and hydrogen, okay, which is going to be, there are 4, so you divide by 4, you get 412. Okay, that's going to be positive 412 to break. Yeah, but I want now for formation. Okay, so it's not 412. Yeah, so it should be negative 412. Okay, negative 412. Okay, because it's formation. Okay, and then how many? Okay, you see 1, 2, 3, 4, 5, 6. So it should be 6 times by 6, and then you add. Okay, so what I will get, okay, so let me calculate fast here. 412 times 6, okay, and then I add 350. I will get negative 2822. Why negative? Yeah, it's bond formation. Yeah, and then to find the overall, okay, it's going to be just add these two, 0 plus negative 2822, and you will get this answer, which is negative. Yeah, that's our answer. Yeah. Now the next question, 17. Element X requires strong heating to react with oxygen. Strong heating, yeah. And then the X reacts with chlorine to give a covalently bonded chloride. So covalently bonded definitely cannot be magnesium. Magnesium chloride is not covalent, yeah. So sodium cannot be, sodium chloride is ionic, yeah. So cannot. So it can be either phosphorus or silicon, yeah. So if you look over there, phosphorus, yeah, when you react with oxygen, they are readily reacting, yeah, so they are quite vigorous reaction. So they say strong heating, so X should be most likely will be silicon, yeah. And then silicon, they react with chlorine to give you SiCl4. This one PCl5, yeah, also can. PCl3 also can. Okay, but they do not require strong heating because it's actually vigorous reaction to give you P4O10. Okay, so this silicon, yeah, when they want to change into SiO2, yeah, you need to react with oxygen and you require to heat them, yeah, strong heating, yeah, to give you this SiO2. So the answer is going to be D. Now 18, the melting points, okay, sodium to aluminium. So when we look into melting point, so sodium, magnesium, aluminium, melting point in this case is the bonding between the atoms, okay, and so on. So in this case, sodium to aluminium, they are giant ionic lattice, yeah. So giant metallic lattice, sorry, yeah, giant metallic lattice. So giant, basically they have metallic bonding. So if they have metallic bonding, so it has to do with the sodium ion. They will give you Na+1 electron will go to the C of delocalized electron, magnesium 2+, and then aluminium 3+. You can see aluminium gives 3 electrons. Each one aluminium gives 3 electrons to the C of delocalized electron. So the metallic bonding, okay, for aluminium is much more greater compared to sodium. Okay, so the factor that affects over here is nothing to do with ionization energy, electronegativity, or increase of AR. It's just 100% depending on the increase in the number of outer electrons, okay, because they will decide how many electrons per atom that will go into the C of delocalized electron, and that will actually help us to predict the melting point. Yeah, the increase is because of that. Yeah, increase of melting point because of more metallic bonding. Yeah. Now 19, the nitrates, okay, of beryllium, calcium, magnesium, and strontium all decompose in the same way when heated. Okay, so if I have beryllium nitrate, okay, so beryllium nitrate, and then calcium nitrate, and then I have magnesium nitrate, and then strontium nitrate. Okay, all of them are going to be from group 2. When they decompose, they will give you the BeO plus NO2 plus oxygen. Yeah, so similar, calcium oxide, NO2 plus oxygen, magnesium oxide, NO2 plus oxygen, and then SRO plus NO2 plus oxygen. So if I want to balance this, yeah, so of course you need 2, so I just put 2 there, each of them, and then this should be half, yeah, so I just put half. Now here they say that when 2 gram of this anhydrous nitrate is decomposed, 1.32 gram of gas is produced. So in this case they say that, okay, the gas, there are 2 types of gas that exist over here. So nitrogen dioxide and oxygen, we need to count them together. So first, okay, we need to find out, okay, how many moles first, yeah. So I have calculated earlier, yeah. So let's say for example, okay, if I have beryllium nitrate 2 moles, yeah. So the MR, okay, MR is 133, okay. So let's say this is 2 divided by 133, okay. So that's going to be the number of moles, okay. So let's actually look into that. 2 divided by 133, so that's going to be 0.015, okay. So 0.015, so number of moles, okay, and we are looking into 2 moles, so double, so 0.03 moles, okay, and then half of it, so divided by 2, you'll get 0.0075 moles of this. So we know that, okay, we can find the mass. So this is 14, and then 16, 16, 32, so that's going to be 44, yeah. So if I times by 44, I can get the mass of NO2. If I times this by 32, I will get the mass of oxygen. So let's times first. So 0.03 times 46, yeah, not 44, 46, okay. So times by 46, you will get 1.38 and 0.0075 times 32, you'll get 0.24. Let's add these two together. So 1.38 plus 0.24, you will get 1.62. So 1.62, okay, not the answer that we are looking for. We are looking for 1.32. So we keep on doing, yeah. So the answer that gives you 1.32 will be the answer. Okay, so you can try all, okay, all this, okay, the MR is given, but anyways, okay, the answer is going to be here. So I'll just show you, okay, this MR, okay, so 2 divided by, okay, the MR is going to be 164.1, so 164.1, so that's going to give us 2 divided by 164.1, so 0.012, yeah, moles. So if you look at double, okay, here 0.024 and half, so 0.006. Okay, so let's actually calculate the mass, yeah. So this one times, okay, 46 like this now, and this one times by 32. So how, let's calculate. So 0.024 times 46, that's going to be 0.1104, and 0.006 times 32, that's going to give us 0.192. So we add those, 0.1105 plus 0.192, 0.115, hold on, 0.1105 plus 0.192. 0.024 times 46. Okay, sorry, this one mistake, yeah. So this one is 1.104, yeah. So I just change here 1.104. Okay, we add with 0.192, 1.104 plus 0.192, you will get 0.192, 1.296, which is okay, 1.296, which is going to be, actually the answer I have rounded off, yeah. So if you use the exact, yeah, if you use the calculator, okay, you will get 1.32, yeah. So if I just use more, okay, let's say 2 divided by 164.1, so 188, let's say 188. Okay, if you use more decimal places and then times by 2 times by 46, I get 1 point. Okay, this one, instead of this, I get 1.12127, and then this one 2 divided by 164.1, and then times 0.5 times 32, .195, so you add with 1.2. Okay, basically you just need to calculate using, yeah, your calculator, yeah, basically. Okay, so this one plus 0.195, you will get 1.31627, yeah. Okay, of course, if you use more decimal places, you will get closer to what they want, yeah. So this will become 1.32, yeah. So that will be the one that we are looking for. So the answer is going to be B, yeah. Now let's move forward. So question number 20. Okay, in the diagram, okay, each test tube contains this 25 cm cube of 0.1 mole per dm cube solution of salt. Okay, so they are added with sodium hydroxide, and then they are added with H2SO4. Okay, so I summarize over here. Okay, so you add sodium hydroxide here, and then you add H2SO4 over here. And then if you calculate the number of moles, okay, so if you use this one, okay, so 0.1 times 25 divided by 1000, you will get this number of moles. Okay, so this number of moles, and then within, okay, the barium chloride, magnesium chloride, and so on, they say 25 and 0.1, the number of moles. Okay, I have calculated the number of moles, yeah. So it's similar, yeah, 0.025, 0.0025. Okay, so they are reacting, yeah. So they say which one has higher pH and which one has greater mass of precipitate. So generally here I have put for W, X, Y, and Z over here. So I have written down the equation, yeah. Sodium hydroxide react with barium chloride, give you this, and you give you this. So this is the precipitate. This one react with this to give you this. This is the precipitate, and this one react with this, so you will get this as the precipitate and you will get this as the precipitate. Now do remember, okay, that for here they do have, okay, they want higher pH, yeah. So when you look at the pH, okay, so anyways here, okay, they use sodium hydroxide, so 2 moles, okay, reacting with 1 mole. So it means that, okay, you have, okay, you require 2 moles of this, okay, double the amount, okay, to react with this. It means generally all the sodium hydroxide, okay, they are used up actually, yeah. This sodium hydroxide is actually the limiting region, yeah. So they are used up, okay. All the 0.0025, okay, sodium hydroxide is used, but they are only half of it. It means this one completely used up, okay, and then only 1 mole, okay, the ratio, yeah. So only maybe 0.00125 moles reacting. There are excess barium chloride, there's excess magnesium chloride, but they do not contribute to the pH, yeah. So, and they are aqueous, nothing to do with the precipitate, okay. Anyway, the idea is, okay, each of them, okay, they will give us sodium chloride, and then barium hydroxide, and then magnesium hydroxide, and then the concentration we will follow the 0.00125, because why? This is 1 mole, this is 1 mole, yeah. So we told that all this is the limiting region, so we use all the 0.0025, okay, from here. So we have, okay, half of it, so it's going to be 0.00125. Okay, the idea is the number of moles of the precipitate is the same, okay, but, okay, if you're looking into higher pH, we just need to look at, okay, which one is more soluble, hydroxide, yeah. So these are group 2 hydroxide, okay. Group 2 hydroxide, as you go down the group, okay, they are going to become more soluble, okay. For sulfates, group 2 sulfates, when you go down the group, they will become less soluble, yeah. So you don't need to know the reason for now in AS, okay. We will learn this in A2, okay. But, okay, if you look at between barium hydroxide and magnesium hydroxide, barium is lower, yeah. So of course they are more soluble. When they are more soluble, they will give more hydroxide ions. So if they have more hydroxide ions, okay, so it means that the pH, okay, will be generally higher, yeah. So the higher pH, we are looking into W actually, yeah. W will have higher pH, okay, definitely not X, okay. So W will have higher pH, and then the greater mass of precipitate. So mass of precipitate, okay, you see, precipitate, okay, all of them, yeah. Even here you see this is 1 mole with 1 mole, so 0.0025, okay, will react with 0.025 to give you the same number of moles, okay. They are the same, all of them, okay. The precipitate is the same number of moles, but, okay, we know that we want the greater mass of precipitate. So it means that we, although, okay, the precipitate over here, they are soluble, more soluble, but barium sulfate or magnesium sulfate, for sulfate, the precipitate, when you go down the group, they are becoming more insoluble, okay. So the higher mass of precipitate should be this one, yeah, barium sulfate compared to magnesium sulfate. Magnesium sulfate is a little bit more soluble, so they can dissolve, okay, but barium sulfate, they don't dissolve. So the mass of, a greater mass of precipitate will be barium sulfate, yeah. So this should be Y, yeah, so not X, Y, yeah. So Y should have greater mass of precipitate, and W should have the higher pH. So therefore the answer is A, yeah. Hope you can understand. So let's actually move on. Okay, question 21. What is the oxidation state of chlorine containing species that kills bacteria in drinking water? Okay, so always remember, okay, Cl2 plus H2O to give you HCl and HClO. So this is going to be the chlorine containing species that they are talking about. So HClO, okay, so if you want to find the oxidation number, hydrogen is always plus 1. So plus 1, okay, plus X plus negative 2. Overall is going to be 0. So X minus 1 equals to 0. X is going to be plus 1. Okay, so the oxidation number is plus 1. Okay, that's the answer. Next. Compound Q is a crystalline white solid that dissolves easily in water. Okay, so dissolve easily in water, yeah. So compound Q, yeah, first of all, you can delete certain things, yeah. White crystalline solid dissolve easily in water. Silver chloride cannot dissolve easily, yeah, it's a precipitate, yeah. So maybe this is possible, this is possible. Okay, this one I'm not sure, yeah, but we can wait. Okay, then they say when concentrated sulfuric acid is added, yeah, steamy white fumes are formed, yeah. So when you add with NaBr, okay, NaCl, PbBr2, okay, whether steamy white fumes, normally we are expecting steamy white fume is HCl, yeah. So generally, most probably HCl, we are expecting HCl. Okay, but if you are not sure, it's still okay, fine, we can skip this part. When these white fumes are passed into aqueous silver nitrate, so the white fume, okay, can be in this case HBr, HCl, and then maybe here is HBr. So these are the white fumes, and then they pass into silver nitrate. A white precipitate is formed. So when you write with silver nitrate, what will happen? You have AgBr, you have AgCl, you have AgBr. So AgBr, okay, and AgCl, what's the color difference? Okay, always remember, AgCl white precipitate, AgBr cream, AgI is yellow precipitate. So we are looking into a white precipitate. So AgCl, we are looking into AgCl. So most likely the answer is going to be C. Yeah. So the precipitate is also soluble in dilute ammonia solution. Yeah. So silver AgCl. Yeah, AgCl. So this one further testing, because AgCl, they dissolve in dilute, dissolve in concentrated ammonia. Yeah. So further reactions. Yeah. So you can read onto that, yeah. But anyway, the answer is going to be C. Yeah. Next question, 23. R is solid. R fizzes when HCl is added. Okay, solid and then fizzes when HCl is added. So fizzes, basically they are going to give you carbon dioxide gas, okay, or maybe sulfur dioxide. But in this case, most likely I can see maybe carbon dioxide. Now R reacts with hot aqueous sodium hydroxide. Okay, so it must be something like acidic. So possible maybe carbonate, okay, carbonate, bicarbonate possible. Okay, giving off a gas that turns red litmus blue. This is basically they are giving you ammonia. So if they are giving you ammonia, it must have ammonium compound, ammonium. So there must be ammonium. So you can see all of them contains ammonium. Yeah, it's not so helpful. So they are asking what is the formula of R. Okay, so I'm going to remove this, yeah, because I'm looking into fizzes means carbon dioxide. Yeah, then they react. Okay, then they give you red litmus paper. Okay, A, B, C can be the answer. Okay, but now they say formula. So let's actually go in detail. NH4 is plus and then CO3 is 2 minus. This is wrong, yeah, so it's supposed to be NH4 2CO3. Yeah, so this is wrong. Ammonium NH4 plus CO3 2 minus, so times 2, so this one is correct. And then here HCO3 is minus, NH4 is plus, so they just put NH4 HCO3. Okay, so this is wrong. Yeah, so here we have found out the answer is going to be B, just directly like that. Now 24. Photochemical smog is a type of air pollution. So this one is a newly added part in the syllabus. It's very new, so they even asked in the new paper. So this one, photochemical smog, is actually produced by PAN. Yeah. So the compound called PAN. This PAN basically contains what? Yeah. So they say the mixture of primary pollutants leads to the formation of photochemical smog. So PAN contains unburned, unburned hydrocarbon, and they also contain nitrogen oxides, nitrogen oxides. So no carbon monoxide, no nitrogen oxide, no. C will be the answer. So just remember PAN. PAN can cause photochemical smog, and PAN contains nitrogen oxide and unburned hydrocarbons. Now 25. T is an element of period 3. So the first ionization energy of T is lower than the element of with one less proton. Oxide of T does not react with water. So if you look at the oxide, sodium oxide, they react with water. So therefore cannot be the answer. Aluminium, they do not react with water. The aluminium oxide, sodium oxide, they react. Aluminium oxide do not react with water. Silicon oxide also no reaction with water. Sulfur oxide, sulfur dioxide, they react with water to give you H2SO3 and so on. So no. So it must be between aluminium and silicon. So they say the first ionization energy of T is lower than the element of one less proton. So if you look at the aluminium, aluminium is 13. So 1s2, 2s2, 2p6, 3s2, and 3p1. So if you compare with the one less proton, so it means they have 1s2, 2s2, 2p6, 3s2. This will be much more. The first ionization energy is going to be, this one is lower. Means this one easily can be removed. Compared to this. Why? Because between the 3s and 3p, 3p is further away. From the nucleus. So because of that, because of the distance, it's much more easier to remove the electron from 3p1. So making this the one before, which is silicon, they mean. Before that is actually magnesium. So magnesium is much more easier to magnesium is more difficult to be removed compared to aluminium. Aluminium is easily can be removed. Why? Because the distance. So the identity of T is going to be aluminium, definitely not silicon. So A. Now 26. The structure of tartaric acid is shown. Which statement are correct? A molecule of tartaric acid has more than one chiral center. So if you see here, chiral center means they have all 4 different groups here. So have double bond. So therefore don't have only have 3 bonds. So not 4 groups. So if you look over here, if we see here, this is going to be a chiral center. Why? Because OH, this different group, and there is H. So 4 different groups. And if you look at this is also a chiral center. So you have hydrogen, this, and this. So this is also a chiral center. So no. So although if you look in detail, they are both of them, have, if you look at this, same chiral center and then another chiral center, which is the same groups here. So you can debate on this, but anyway, if you look at the molecule as a whole, it has 2 chiral center. So if you have 2 chiral center, so here a molecule of tartaric acid has more than 1 chiral center. So this is correct. Then the molecular formula of tartaric acid is C4 H4. Yeah, so if you look over here, there's 1, 2, 3, 4 hydrogen, but do remember there is also hydrogen here, sorry, hydrogen here, there's hydrogen here. Okay, so it's supposed to be C4H6. Yeah, so that is wrong. One molecule of tartaric acid produced 4 hydrogen ions. Okay, supposed to be, okay, if you look at here, they say 4 hydrogen ions. Okay, 4 hydrogen ions in aqueous solution. Okay, so one molecule of tartaric acid, 4 hydrogen ions. So here, this is alcohol. Okay, so this is carboxylic acid. So if it is aqueous solution, so only the carboxylic acid group is the one that will give us the hydrogen ion, not the alcohol. Okay, so we are talking about 2, not 4. Yeah, so only 2. So the answer is going to be 1 only. So the answer is going to be D. Now 27. So carboxylic acid P has no chain isomer. It reacts with an alcohol Q that has only one positional isomer. Okay, what could be the ester form between reaction P and Q? So if you look over here, okay, so they say that P, the carboxylic acid, has no chain isomer. So you can see maybe they have only one hydrogen, okay, maybe like this, or they can have 2 carbon, okay, or they can have 3 carbon. Okay, up to 3, okay, they don't have any chain isomer. But if you have 4, okay, then they can have chain isomer. Okay, if you have 4, so what will happen? This carbon can still come over here. Okay, they have chain isomer. So we don't want that. Okay, according to the question, they don't want that. So it can be either these 3. And then it will react with alcohol that has only one positional isomer. Okay, when you look at this, okay, one positional isomer, it means it can be alcohol. So the alcohol is going to be, maybe if you have one carbon, OH, okay, so this one, no positional isomer actually. Yeah, no positional isomer. So cannot be 1 carbon. So let's say we have 2 carbon. If I have OH, this is also, okay, no positional isomer, because OH, anything. So it will be only they want 1. Yeah, so this is going to be no positional isomer. Yeah, so must be something that has 3 carbon. If I have 3 carbon, if I have OH here, I can also have one more, okay, possibility of having the OH here. So that is going to be 1 positional isomer. Yeah, so only 1 positional isomer. Okay, so most likely 3, but let's actually see whether if you have 4 carbon, whether it is applicable or not. Okay, so if you have 4 carbon, if I have OH here, I can also have the OH here. Okay, OH here is still the same. So this is also possible. Yeah, so 4 carbon also possible, 1 positional isomer. Okay, so what could be the ester form between P and Q? Okay, the ester that can be formed, so you see alcohol. Okay, alcohol will give you the YL. Yeah, so it can be either propyl. Okay, if you look at propyl, yeah, possible propyl, and then propyl pentanoate. Yeah, pentanoate, wrong. Yeah, because we must have either 1, 2, or 3. Okay, maximum propanoate. Yeah, so this one definitely not the answer. So let's explore further. Yeah, cannot be ethyl, because ethanol, okay, ethanol is not here, because ethanol do not have any positional isomer, so cannot. So pentyl or butyl, yeah, pentyl will not be our answer, because pentyl you can have more than one positional isomer. Yeah, so butyl will be this one. Okay, butyl. Okay, butanol, and then propanoate. Yeah, 3 carbon. Okay, for carboxylic acid. So the best answer over here is A. Okay, now next, which pair includes a hydrocarbon without a chiral center? Yeah, so here you need to check. Okay, the question is not so clear. Okay, because they say which pair includes a hydrocarbon. It means within this pair, okay, within the group A, B, C, D, there is one, okay, that can contain something that has no chiral center. So if I look over here, you can slowly do it at home. Okay, so I managed to find this is a chiral center. Okay, and then managed to find that this is a chiral center, this is also a chiral center, so cannot be our answer. Okay, this one is a chiral center, chiral center. Okay, this will be a chiral center, chiral center. How do I do? Yeah, so you just see this chiral center means the carbon is attached to 4 different groups, so cannot be chiral center, cannot be chiral center, cannot be chiral center. CH2, hydrogen and hydrogen cannot. So this one, like for example CH, there is CH, and then this entire 3, so I just put it over here, and then there is CH3, and then CH2, which is C2H5. So you see 4 different groups, so I just find out that this is going to be a chiral center. So you do the same thing. Yeah, you will notice that all these combinations, they have chiral center, except, okay, for this they have chiral center, but this do not have any chiral center. Yeah, why? You see carbon, hydrogen, CH3 cannot be. Okay, and then this carbon contains H and H, cannot be. This carbon, that is C, H, and then CH3 cannot be. Yeah, so there is no chiral center here, so it means the best answer over here is D. Yeah, check again. Yeah, you need to draw, okay, but the answer is going to be D. Now, what is the major product form when compound R is warmed with excess HBr? Okay, when you warm this with excess HBr, okay, what will happen? Okay, they are going to be this OH. Okay, they are going to be substituted by the Br. Okay, so of course you'll have Br. Okay, so here Br, but do remember, okay, HBr, they will also go here. Okay, the double bond is going to be broken, so the H, okay, will go to the carbon that contains the most hydrogen. So if you look over here, this carbon, okay, 1 bond, 2 bond, 3 bonds, so one of it must have hydrogen. So 1 bond, 2, 3, 4 bond don't have hydrogen. So you see directly attached to it, this carbon don't have hydrogen. This carbon has, okay, directly attached to 1 hydrogen, therefore the hydrogen will go to this carbon. Okay, so hydrogen will come here, Br will go here. So if you look over here, yeah, Br will go there, not here. Yeah, so the answer, okay, here, okay, if you look over here, Br, okay, Br cannot come here, it will go to the top. Yeah, so I don't select this. Okay, this one will not be the answer because must have Br2, Br here. So the answer is going to be A. Okay, now next, 30. So you have cis but2-ene reacts with cold dilute acidified potassium manganate solution to give product X. Okay, and then the cis react with hot concentrated to give product. So basically when you react with cold, okay, so this will give you the product X is actually going to give us diol. Okay, so you will have the OH and OH. Yeah, so there will be diol. And then for Y, okay, hot condition. So if you have hot condition, the double bond is going to be broken. So you have one R group, okay, so you will have C double bond O, you have CH3, and then this one hydrogen, then further oxidized to give you carboxylic acid actually. So you will have carboxylic acid. So here the product is a diol, and this is a carboxylic acid, two same carboxylic acids. Okay, so which role correctly describing? So when sodium metal, so do remember diol, okay, alcohol can react with sodium. Carboxylic acid also can react with sodium. So both of them, they will react. Okay, both of them, they will react. Okay, both of them, they will react. And then for sodium hydroxide, do remember alcohol, okay, do not react with sodium hydroxide. Yeah, so only carboxylic acid react with sodium hydroxide. So only this. Yeah, so the answer is going to be B. Okay, next. For which reaction will the major product have the lowest relative molecular mass? Okay, so you have bromoethane. Okay, bromoethane. So let's see, bromoethane, 1Br. Okay, then you react with sodium hydroxide. So what will happen? This will be replaced by OH. Okay, and then bromoethane with sodium cyanide and ethanol. Okay, so bromoethane, the Br, so now this one will become Cn. And then 2-bromopropane heated under reflux, okay, with eco-solution of sodium hydroxide. So propane, bromo, now hydroxide, so this one will be OH. And then 2-bromopropane is heated, okay, ethanolic sodium hydroxide. So if you have bromopropane, so what will happen? Okay, the hydrogen from here, they will be removed. Yeah, it's an elimination reaction. So C double bond C. Yeah, so what we are going to do is to find out the relative molecular mass. Yeah, so maybe if I write everything full, okay, so C2, so that's 24 hydrogen, 1 2 3 4 5 6 hydrogen, okay, 6, and then 1 oxygen, so 16. So that's going to be total of 30 plus 16, 46 over here for A. And then here there is H, 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 and H. So 3 carbon is already 36, nitrogen is 14, 1 2 3 4 5 plus 5, you already get 55. Okay, they want the lowest. Yeah, so here 3 carbon, 36, 1 2 3 4 5 6 7 8, and then with oxygen, so 44 60, and then the last one 1 2 1 2, so 36 carbon, 3 carbon, so hydrogen 1 2 3 4 5 6 6, total 42. So they want the lowest, so 46 55 60 and 42, so 42. So this will be the answer, the lowest. Yeah, now next 32. So you have C4H9Cl reacts with warm dilute aqueous sodium hydroxide solution. Which isomer will form the most stable cation intermediate? So basically you have one chlorobutane. Okay, this is one chlorobutane, two chlorobutane, and then one chloro, two methyl propane. So propane, one chloro, two methyl, and then here is two chloro, two methyl propane. So what we do is before they actually react with sodium hydroxide, basically they will form a cation intermediate. So this Cl, the one that has Cl, will become the positive. So it will become positive, they will become positive. So if you look over there, you will notice that, okay, they have one R group only. Okay, that's one R group only, so it's primary. And then if you look over here, there is two R group, that's going to be secondary. If you look over here, H, so only one, okay, R group, primary. And then here there are three, so tertiary. So of course, if you look at the stable carbon in a cation intermediate, so the tertiary is more stable compared to secondary and primary. Yeah, so this one is something to do with positive inductive effect. Yeah, so the inductive effect, okay, will make, okay, the cation intermediate to be more stable. Yeah, so we will choose the tertiary. Yeah, tertiary is more stable, so tertiary will be selected. So here, okay, the answer is going to be D. Okay, next 33. Yeah, let's move on. So 1 mole of organic compound requires 6 moles of oxygen for complete combustion. Yeah, so this one, okay, if you look at it, okay, like for example, butene, yeah, put one in, okay, C4, okay, H8, okay, butene. When they react with oxygen, they will give you carbon dioxide and water. So they must give you 4. Hydrogen is 8, so must be 4. So if you count here, total 8, 12, so 6. Yeah. So it means this one 6 moles possible. Okay, if you have 4 carbon. How about butane to all? Okay, let's try. Butane to all, so they have like this, okay, OH, so it's going to be C4H 1 2 3 4 5 6 7 8 9 H9 OH plus oxygen, okay, to give you carbon dioxide plus water. So if we balance this, okay, this is 4, okay, 4, and then hydrogen is 10, okay, so I need to have 5. So how many oxygen? 5 plus 8, so 13, okay, 13. So 1 is here, so 6 also. Yeah, so 6 moles. So possible to have butane 2 also. Yeah, but definitely cannot be propane 2 all. Okay, why? This one is also possible. Yeah, but propane 2 all, you just see C3H7OH, okay, plus oxygen to give you carbon dioxide plus water. So if 3, so I put 3. This is 8, so I need to put 4. So how many oxygen? 4, and then 6. 4 and 6, 10. Okay, 10. So this is 1, so this should be 9/2. So it's not giving you 6 oxygen, so definitely this is wrong. This is possible because methyl propane 2 all is still butane. Yeah, butanol. Yeah, possible. Okay, but let's actually see. We have eliminated C. Okay, and then 1 mole of J reacts with sodium. Okay, so reacting with sodium, automatically alkene do not react with sodium. Okay, so alcohol, okay, do react with sodium. It gives you hydrogen gas, so possible. and then J reacts with the excess, okay, J react with the excess hot acidified potassium manganate to produce a compound which gives an orange red precipitate. So this one can be either aldehyde or ketone, yeah, carbonyl compound. So it must be oxidized, okay. So if you look at this, okay, the butan 2-ol, okay, butan 2-ol, okay, if you look over there, okay, butan 2-ol, okay, this is OH, so we see it's going to be 1,2 secondary alcohol. Secondary alcohol, okay, if you try to oxidize, okay, secondary alcohol, they will change into ketone. Okay, they will change into ketone. But if you look at this 2-methyl propan 2-ol, okay, propan 2-ol methyl, okay, this is going to be a tertiary alcohol. Tertiary alcohol cannot be oxidized. Yeah, so if they cannot be oxidized, they will not give you aldehyde or ketone. So in this case, this is going to give you ketone, okay, and therefore they will give you the orange red precipitate with 2,4-D and pH region. Yeah, so the answer is B. Now 34, a structural isomerism and stereoisomerism should be considered when answering this question. So they react with hot concentrated sulfuric acid to form several isomeric compounds, okay, with the formula of C7H14. So when they react, okay, basically hot concentrated sulfuric acid, so they are going to be like a hydration reaction. Yeah, so they will remove, okay, the H and OH. Yeah, so when you remove, okay, they are going to be certain double bonds are going to be formed. So if we look over here, may be difficult to see. Okay, so first of all, okay, try to write it down, yeah, in terms of displayed formula and so on. So when I wrote it down, okay, I know that, okay, here there is, okay, I'm just taking this 3 carbon, so I just put C3H7, okay, C3H7, and then there is going to be carbon here, okay, so this is the carbon, and then there is OH, and then there's CH3 here. So what I do is the hydrogen from here and the OH, they can be eliminated to give you the double bond here, and then left with this, okay, left with this, okay, 2 carbon, so 2 carbon, okay, left with this. So you'll get this structure. Now apart from that, okay, what will happen, you can also have the OH, okay, will be removed, okay, the hydrogen, okay, earlier came from here. The hydrogen can also come out in from different, okay, instead of CH3, maybe they come out from here, okay. So if they come out from there, okay, you can have, okay, so this one we did just now. So let's say for example you have CH3 and hydrogen, CH3, so so let's actually see from here, yeah, so OH, and then the hydrogen comes from here, from this carbon, yeah, so the double bond goes around here, yeah, so I'll just erase a little bit. So CH3, and then this entire thing will stay, okay, so CH3, C3H7 stay, and then this part, the OH, okay, that was removed, and then one of the H will be removed. There is a CH3 here, so that's why the CH3 is here. Okay, you need to draw it again, yeah, to show, and then there is a double bond over there. That's another possibility. Okay, another possibility is, okay, rather than previously you took the hydrogen from here, so rather than that, okay, you can actually take the hydrogen directly from here, okay, which is going to be if you have the C, okay, this entire thing is C2H5, and then there is hydrogen. Hold on. One, two, three. So if I take the OH, I bring it over here, then the H from here, so I remove from here, yeah. So the double bond comes here. So how it looks like, so it will have carbon, double bond, another carbon, and then there is H, this is 2, so C2H5, and then there's CH3, and then this is 2 carbon, so here you have 2 carbon, okay. Double carbon, okay, this is the carbon, there is CH3, and then another 2, H, and this CH3, okay, correct. So you will get, okay, these 3 possible combinations, okay, you just go through. Now when you look over there, the double bond over here, you see this carbon attached over here, same groups, they do not have cis and trans, yeah. So in order to have cis and trans, they must have 2 different groups attached to the carbon that is attached to the double bond. So they do not have cis and trans, so they only have one possibility, yeah, one stereoisomer, and then there is no no chiral centers over there. And then if you look over here, okay, there are 2 different groups, so there is possibility of having cis and trans, so 2, yeah. And then here similar, you have 2 different groups, possibility of having 2, so total, okay, they must have 1 plus 2 plus 2, so total 5, so 5 isomeric compounds, yeah. So please check again, okay, this one you need to spend some time to do, yeah. Now the next, okay, the table shows a student's prediction of the reaction of 3 compounds. So this one is an aldehyde, is a ketone and ketone. So alkaline I2, yeah, basically this one is going to be triiodomethane. So triiodomethane, as long you have CH3 group, yeah, possible. Okay, you have CH3 group, possible, and then there is no CH3 group, methyl group, so no reaction. So possible. Now Fehling and Tolan, okay, they give you positive results only when we are dealing with aldehyde. Ketone do not have any positive result. So aldehyde, yes, positive. Ketone, no, so correct. And then ketone, no. So it means all of them, okay, is correct. Yeah. So the answer is A. Now for 36, which mechanism describes the reaction of aldehyde and ketone with ACN plus NaCN? This one is very easy, yeah. So carbonyl compound, they will undergo nucleophilic addition, yeah. So nucleophilic addition, C. Now propyl propanoate can be synthesized in 3 steps using propylnitrile as the only organic starting material. So in step 1, the nitrile is converted into compound X, okay. So step 2, compound X is converted into compound Y, and step 3, compound Y is reacted with more of compound X to give you propanoate. So first step, okay, what they do, okay, they change this, okay, with to become carboxylic acid. Okay, so to change into carboxylic acid, you need to change the nitrile to become carboxylic acid by using ACl. Okay, so you react with ACl. Okay, that's going to be our step 1. Step 2 is the carboxylic acid. They need to change, okay, to Y. So this one is actually you need to change it into alcohol. Yeah. So how do you change into alcohol? You use reducing agent. So reducing agent, if you use LiAlH4, okay, they will change into primary, the carboxylic acid will change into primary alcohol. And then after that they say 3, compound Y, which is compound Y, the alcohol, okay, they react with more of compound X, which is going to be our carboxylic acid. So you will get this propyl propanoate. Okay, so you will get this ester. Okay, therefore, okay, this should be the answer. 38. The ester is hydrolyzed by boiling with sodium hydroxide. So when you have this ester, yeah, so when I do breaking or the hydrolysis, you separate, and then you are going to have sodium hydroxide. So the NaOH, okay, the hydrogen will come over here, and then the NaO will go here, NaO, yeah. So what will happen? This will give you methanol. Okay, so there is no methanol here, and this one will give you CCC double bond O, O minus, and Na. So 3 carbon, so sodium propanoate, yeah, sodium propanoate. This will be the answer. Sorry. 39. Compound V polymerizes to form polymer W. A section of polymer W is shown. So when I see this section, when I repeat again, Cl, Cl, then you have C, Cl like this, and then it repeats again. So I just put this is the repeating pattern. So if it is repeating pattern, this arm fold it back, this arm fold it back to form the double bond. So you get double bond, Cl, Cl, so you put up and down, and then this, there's hydrogen, and then Cl, sorry, not hydrogen. Normally if they don't see write this C, CH3. Okay, so this one CH3 and then Cl. So this is going to be the monomer. Okay, so what is the correct name? So if you name this 1, 2, 3, okay, so it's propane or propene. Okay, so propene, you look for propene, so propene, and then there's trichloro, okay, at position what, 1, 1, 2, so 1, 1, 2 trichloropropene. So the answer is C. And finally 40. So a molecule of organic compound contains 3 carbon atoms and shows a strong absorption at 1720, yeah. So 1720 maybe here, okay, or here. So they have C double bond O, yeah. So it can be carbonyl, carboxyl, or ester, okay. And then P is reacted with excess hot potassium dichromate, so forming organic product of Q, okay. So when you oxidize, okay, in this case carbonic compound cannot be oxidized, carboxylic acid cannot be oxidized, ester, okay, cannot be oxidized, okay. So they say P is reacted with excess hot acidified, okay. So this one carbonyl compound, okay, maybe carbonyl compound we are talking about oxidized. The only thing is aldehyde, I think, yeah. Aldehyde, if you oxidize, okay, they can be oxidized to become carboxylic acid, yeah. So maybe this one carboxylic acid. So Q shows 1700, so 1700, and then strong 2800, so around here, maybe here, so carboxyl, so carboxylic acid, yeah. So probably, okay, they are going to be forming carboxylic acid. So most likely, okay, because it's 3 carbons, so you see propanol, propanon, propan 1 all and so on, but we don't select this because, okay, previously they say C double bond O, yeah. Okay, so of course it must be either propanol or propanon, yeah. and then after that they must be something that can be oxidized. So propanol cannot be oxidized. Okay, so it must be propanol oxidized to become propanoic acid. So propanoic acid is the one that gives you the carboxyl group, which is from here, yeah, the strong broad resorption. So this one will be, the best answer is going to be A, propanol. Yeah, so that's all. Okay, we have done, okay, 40 questions. Okay, October, November 22. Yeah, see you. Okay, October, November 2022. Yeah, variation 1, 2. Thank you everyone. Bye.